Hello everyone. Thank you very much for watching this video. I'm going to talk about our group machine learning final project, which is CitiBike transportation management. Nowadays, the bike sharing system has gradually become an important part of the urban transportation system. CitiBike, a bike sharing program launched by the New York City government and sponsored by Citigroup Incorporation, is one of the most popular bike-sharing systems in the world. Generally speaking, a public bike-sharing system is that it allows users to ride rented bicycles from one station to another. However, CitiBike's popularity also resulted in a high demand that some stations regularly lack bikes, which other stations are completely full, making it hard to take or park a CitiBike. Therefore, to avoid such problems, dozens of rebalancing teams, for example, like trucks and bicycle trailers, are used to reallocate bikes by shuttling bikes among full and empty stations. In our project, the most significant objective is improving CitiBike transportation management. In other words, we need to deal with the rebalanced situation. To be as an administrator of CitiBike, we want to optimize the bike reallocation problem by raising the following three questions. What is the total number of bikes being used in the system at any time? How do the bikes fall in or out at a given station at any time? How to reallocate bikes between stations due to unbalanced in or outflow? Here is our data source. The CitiBike trip data set comes from CitiBike's official website. The NYC climate dataset comes from NOAA, which is National Center for Environment Information. We will see the detail of these two datasets in the following pages. This is the CitiBike trip dataset. It contains the information about trip datasets like trip duration, start time, stop time, and bike ID. It also contains the information about start station and station like their station ID, station name, station latitude, and station longitude. This is climate dataset. We only use temp, which means temperature, the SPD, which means wind speed, and PCPO1, which means rainfall index. We only use these three indexes in this dataset. Here is our algorithm. We do regression on total number of bikes, and we do regression on inflow or outflow of bikes at one station. What's more, we do SVM to predict inflow or outflow of bikes at one station. SVM is support vector machines which analyze data used for classification and regression analysis. Finally, we do clustering. Clustering is an algorithm for clusters analysis, which is a method for statistical data analysis. Here, we do regression on total number of bikes. Firstly, since the data in original dataset is per travel, we transfer the data into per hour. We introduce two dummy variables, time of the day and the day of the week. What's more, we also introduce some explanatory variables like temperature, wind speed, and rainfall, as we discussed before. Finally, we need to build multi-variable regression models. Here is the result of regression on the total number of bikes. We can see the R-square and adjusted R-square is around 65%, which means the model explains most of the total numbers of bikes, and training the test MSE is larger because the response variable has a large schedule. Secondly, we do regression on inflow or outflow of bikes at one station. Here we introduce net flow, which equals to inflow minus outflow. Since there are 498 stations, we just choose 10 random stations. Then we build multi-variable regression model. This is the result. We can see that this regression model cannot explain the net flow well enough. This is because the inflow or outflow at one station is gradually not stable, and it may be affected by many random factors that is hard to capture. In the third part, we use SVM, the support vector machine, to predict inflow or outflow of bikes at one station. Instead of predicting the numbers of follows, we try to predict if the station has a follow, inflow, outflow, or a balanced flow during a time interval. To achieve this, we categorize the follows into three catalogs: -1, 0, and 1. The result of this SVM method is much better than regression, but still needs improvement. Therefore, we will try to do the prediction on clustered datasets. Since temperature, weather, and time of the day and the day of the week would be more likely to impact a group of stations rather than a single station, to predict the inflow or outflow after clustering seems more reasonable. Comparing to predict the inflow or outflow for just one station, predicting for stations in group might stabilize the inflow or outflow across stations, which might have a better predicting result. Here is two graphs. The left graph represents average cohesion with clusters. The right graph represents the average separation with clusters. Here is the result of regression on inflow or outflow of bikes of clusters. As we can see that the most of the R-square and adjusted R-square are larger than the regression method, which means after clustering, the performance of regression model is better than individual regression. But in general, since the R-square and adjusted R-square are still relatively low, we should use other methods. The method we use is super vector machine to predict in or outflow of bikes of clustering. We can rerun the SVM method on stations as we can see that in general, the performance of SVM on clusterings are better than on single stations. This is the station maps in clustering. In the end, the primary conclusion we achieve is that first, the gradual regression method to predict the total number of bikes being used in the system work well. Secondly, the regression model to predict the night flow of different stations does not work very well. Third, the multi-class supervector machine worked better than regression, but still need to be improved. Finally, after clustering, both regression and multi-class supervector machine on clusters are more likely to perform better. However, there are still some problems we need to fix. One problem is that the model underestimation for the first quarter in 2015. And another problem is that missing extreme peaks during summer. The third problem is that high level of out-of-sample loss for some clusters. As far as we are concerned, by adding more explanatory variables like snow days, holidays events, and big events to improve our models may get more accuracy result. Thank you for everyone watching this video.